Hi, I'm Mark Ritter. I'll be talking today about a project I worked on to reduce the memory footprint of a system written in Go and avoid a costly rewrite in Rust. I'm currently a founding engineer at Akita Software working on API-based observability. I previously co-founded Tintry, which makes VMware flash storage arrays, and worked for a couple of years on the Vault team at HashiCorp. I'm very interested in tools that help developers with performance and correctness problems. So what was our performance problem? Let me tell you about this issue that arose last year. Akita captures live traffic from the network, reassembles it into TCP streams, parses any HTTP content we find, translates it into our custom intermediate representation, obfuscates the values that we find inside the payload, and uploads it in batches to our backend servers for analysis. This runs on customer equipment, so we need to be good citizens of their CPU and memory. When I joined the company, we were transitioning from run us during continuous integration tests to run us all the time in staging and production environments. So of course people ask, how much memory does it need? And our answer was that it usually needed very little, but sometimes multiple gigabytes? This was not okay, not even 1% of the time. So our goal was to get this agent to a state where it was using a predictable and stable amount of memory so that our users would be able to trust us to run in production environments. So our client was written in Go, and we talked about what were our options. Could we live with the problem? Our focus was primarily on learning the structure of an API, so crashing and restarting once in a while could be okay. We were running as a container in a Kubernetes environment, so we could impose a hard limit on the container's memory usage. But the system administrators we were working with gave negative feedback on this idea. They said that their systems tended to misbehave when a hard limit was reached. They needed our process to police itself. But Linux doesn't really let you limit your own RSS. It is not in a while. Resident set size, it's not in a while. And the Go runtime creates a 16 gigabyte virtual memory space for its heap with no way to limit that. So we could rewrite the whole thing in another language which gave us better control over memory allocation. Rust was really the front runner here, and we'd read countless stories about other teams making this choice. But this effort would really be substantial. My estimate was about 3 months, which really means probably more like 6 months. And there's no guarantee that at the end of it, we wouldn't be making the same sort of mistakes. Just because memory management is explicitly controlled doesn't mean you automatically make better choices. In addition, there didn't seem to be anything in the Rust ecosystem that handled TCP reassembly as well as GoPacket, which is a pretty efficient library. And we'd already expended some effort fixing bugs in it. I wasn't eager to reintroduce those same bugs by implementing the TCP reassembly code ourselves. And so this left find and fix everything that needed to be fixed. But the scope of work on this was very unclear. We didn't know where the problems were. There might be a lot of them, and in fact this turned out to be the case. But we decided we would start a time-bounded effort to find and fix the problems. I would work on it for a few weeks, see what I could do. So to understand our memory footprint, we had to understand both the behavior of Go's garbage collector and the behavior of our workload, of our agent. So Go's design is oriented around making garbage collection as painless as possible so that it doesn't add latency to your application. And it does a pretty good job of that. You'll hardly ever notice a major slowdown due to garbage collection pause. But another part of the design is to provide as few controls as possible. The only one you've got controls when garbage collection starts. The Go GC setting defines when memory reclamation will start based on how much memory has been allocated since the last garbage collection phase ended. So for example, if your heap has 200 megabytes of live data, the default setting is that the garbage collector will let you allocate 200 megabytes more before it runs again. So we could turn this knob down and get somewhat lower peak usage at the cost of more CPU overhead, but we weren't getting gigabytes of excess memory usage just because the garbage collector didn't start soon enough. But the thing to note is the choice of Go already puts us in a 2x hole by default. By the time garbage collection starts, there will be as many bytes of new allocation as there were live memory. So even if usage is fixed, the resident set size will be about 2x larger than our heap allocation. And I should mention that in the most recent Go release, 1.19, there's a second parameter which just lets you set the maximum desired, and it tries to stay below that. But that wasn't available to us last year. Fortunately, though, Go comes with a profiling tool that's pretty good, and it's easy to enable. It can tell us two things: the size of the live heap at the time a measurement is taken, and the total number of allocations since the program began. Each of these measurements is associated with a call stack, so we can build a tree with the pprof tool showing memory hotspots. Unfortunately, sometimes what you need to do is find the small object that's keeping a large object live. The Java ecosystem, in my experience at least, has much better tooling for this use case. I looked at some examples from our own environment when the CLI agent had reported high memory usage. The first thing I found when looking at heap usage was some memory that Go packet was allocating. It turns out that instead of allocating memory directly for TCP reassembly, Go packet uses an internally managed page cache. And worse, the version we were using didn't ever free memory. So what would happen is we drop a packet, and the stream would keep going, and the TCP reassembly layer would keep buffering and buffering, hoping to see that missed packet again. And we can allocate a large amount of memory before we give up. So our first set of fixes targeted this obvious problem. We limited the total amount this page cache could use and the amount of reassembly buffer allowed per connection. We upgraded to a newer version of the Go packet library that used Go's sync.pool for pages, which meant that they could be reclaimed. Might not help with spikes, but it would at least mean we didn't stay high forever. And we more aggressively expired TCP connections and flushed the partial data that we did have to the next layer of our parser. This helped a lot. We weren't at 6 gigabytes anymore, but it wasn't a complete solution. 1 gigabyte is still not very good for the amount of work we're doing. And there's still a lot of variance here. It's unpredictably high rather than consistent. So since there were no more obvious hotspots left in the live heap, I switched to look at total allocations. And there's a lot going on here in this sample from the pprof tool. There's an obvious hotspot responsible for a whopping 38% of allocations, and that's in our visitor that's performing obfuscation. At the time, I didn't even know what the heck pack eface was, and I am totally grossed out that time parsing is allocating so much memory. I did not end up rewriting the time parsing library, but it still grosses me out. The cumulative column shows allocations for this function and all its called functions, and that reveals another hotspot. Our object hasher, which I'll talk about later, is allocating quite a lot of memory, more than Go packet itself. We want the memory allocation to be mainly Go packet. We're watching network traffic. We want most of our allocations to be that network traffic, rather than all this overhead. But the other thing to note is there's a disconnect with what I actually want to know. The profiler is telling me hotspots that are allocating lots of memory, but are they actually contributing to increases in memory use? Or is the garbage collector being effective at reclaiming these allocations? So here's an example of the debug log that the Go garbage collector sends. You can turn this on and see what it's up to. There's a bunch of information here, but what I noticed is that the heap was 88 megabytes when garbage collection started, and 102 megabytes when the scan ended just 79 milliseconds later. So, this is not in the gigabyte range, but still 1/5 of our heap was allocated while the garbage collector was scanning. That's what drove the increase. That's what asked for more memory. How do I find what's doing that? And so the middle part of this project was very frustrating. I could see the memory performance getting better, but it did not seem to move us any closer to our goal of stable, predictable performance. Allocation hotspots would drop off the graph. For example, I found a place where we were reinitializing regular expressions every time and made it a one-time init function. Our visitor that performed obfuscation turned out to be allocating objects on every recursive step, and it made a lot of those. And so some of these could be pre-allocated, or we could change the allocation so it was done only when it was needed rather than pre-allocated on every step of this process. But the conclusion I drew is that the garbage collection was actually handling these sites of high dynamic utilization just fine. The data wasn't alive for long. The garbage collector was keeping up with the high rate of allocation. They weren't what was causing our spikes. So here's an example of sort of the frustrating process this can be. Fixing the visitor's append path hotspot moved it from 27% of allocations just down to a bit more over 4%. That was great. But some of that usage popped up in another place that just wasn't visible before. Enter struct had been just a few percentage points more, so there was more work to be done here. What I really wanted, though, was a tool that I didn't have. I wanted to know which allocations were most likely to cause an increase in the overall resident set size of the application. I don't care if I allocate a lot of memory that the garbage collector just immediately reclaims without problems. I do care if I have to go to the operating system for more memory, increasing the agent's footprint. And so the solution I came up with was try to simulate this hypothetical tool by grabbing allocation dumps every minute. I'd wait for a spike. I can see that in our Datadog monitoring. Go back to the minute-by-minute samples I've collected and look at what has been allocated within that particular time period. And those are the candidates for what actually caused the increase. And by looking at several samples of this sort, I could get a better idea of what I should be focusing on. So I mentioned there was a hotspot that showed a lot of cumulative memory usage, and this was in a library called object hash proto. We hash our intermediate representation a lot, maybe too much, but it's useful for deduplication and for keying objects that don't have a natural order. The library object hash proto used reflection to identify what was in each protobuf object. But we had a lot of nested objects, and so as a result, we did a lot of reflection. And it turns out that reflection is not just CPU intensive, which we could live with, but memory intensive, which it turns out we could not. Visiting each struct caused memory to be allocated by the reflection layer, not even by object hash itself. And so after a lot of angst, I finally decided to bite the bullet and completely replace this library. But I had to do so in a way that preserved existing behavior. Having the new hashes different than the old hashes would cause all sorts of problems I didn't want to even think about because, we had old hash data in our database. I did not want to have a flag day. So I wrote a code generator that followed the exact same sequence of operations that object hash proto did, preserving the hash value, but on the concrete protobuf types we were using. So one hash function was emitted by this code generator per protobuf type. And the result was very encouraging. You can see a micro benchmark here. We're about twice as fast, and we only use 38% of the previous memory allocation in terms of bytes. We're a little less good at improvement in terms of allocations. And this was the first fix that really moved the needle. It was an immediate qualitative difference in the first few hours of testing. I was plotting the memory usage by version every time I rolled out a new release candidate with a new fix. And this was the first one where I could sort of eyeball it and say, yes, that was really a big source of our problems. And that sort of gave me the feeling that yes, we could make this work, because I was really starting to doubt it. So after observing for a while longer, I identified another source of spikes. In this example, 50% of the allocations in one of those minute-to-minute samples came from just one function. And this turned out to be a large HTTP response that was compressed, and we were decompressing it into a buffer before parsing the body. So I did two things to fix this. One, we streamed from the compression function directly into JSON parsing, which accepts a reader, so that was easy. And we limited the maximum size of a response we attempted to decompress to about 10 megabytes. And the other thing to note is that all the cruft which was above Go packet operations is now below it in this profile. We're spending memory mainly on the things we have to spend memory on. So what did I learn from all this? I ended up having to touch 3 out of the 5 phases I mentioned. The things I thought it might be, such as too much buffering before upload, maybe we had to switch from, switch to a smaller number of objects in each API call we made to our backend. All that turned out to be irrelevant. It was not where I thought the problems might be at all. It took about 25 days of effort altogether. So our decision to explore this path paid off, but it was still a very expensive fix. The results were good enough. It's still a kind of a hefty process for an observability tool, but it's a lot more predictable. On our own dog fooding system, we measured the 99.9th percentile of resident set size was less than 280 megabytes. This also tells us that there really wasn't a huge win from a potential Rust rewrite. As I mentioned before, Go's default settings sort of give us a 2x blow up from our actual heap size to our resident set size. So if we adopted the same general architecture, we'd still be at 140 megabytes, which is better, but it's still not small. If somebody's trying to put us into a 1 gigabyte container, that's still more than 10% of the overhead. And unfortunately, the story doesn't end here, because we found new cases that caused spikes and memory usage started creeping back up again as we asked our agent to do more things. But this measurement was good enough to go work on something else for a while. The user we were working with said, yes, we can deploy this in production. This looks good. So, one of the things we did that didn't help with the stability was still a good idea is reducing the fixed overhead, because every live byte in the heap cost 2 in a resident set size, and it made it a lot easier to focus on what was actually being allocated. We needed to profile allocation, not just the fixed data. And most memory leak how-tos are about how to find why you're using too much memory. We had to fix why are we allocating too much memory. One of the ways we fix that is by streaming rather than buffering. I mentioned that the JSON parser can accept a reader, which is great, but it also produces all its output in a single object, which is less great, and we may have to fix that in the future. The thing that caused the most friction with the way Go idioms work is replacing small, frequent allocations. You can find what we did in our open source repository. It's not very pretty. Go really pushes you towards, oh, well, just allocate a small slice to do X or allocate a map to do X, and those add up. And part of that is understanding your libraries. I don't mean you should avoid libraries at all, but maybe avoid libraries that that use reflection or use some other indirection mechanism that's going to be high memory cost. So we replaced the sort of generic library that worked with any protobuf with code that worked only with our protobufs. And so, unfortunately, performance is not something that hides behind an abstraction barrier. If the library used is going to allocate a lot of memory, you're going to have to deal with that, and that may cause you to make a different choice. And finally, I think the most important was to find a way to simulate the tool that you wish you had. That was really the breakthrough, is when I stepped back and said, pprof as it's standing today isn't giving me the information I want, but I can derive the right hints from it if I use it in the right way. So thanks for attending. I'm Mark Gritter. You can reach me on Twitter with any follow-up questions, or visit Akita Software to learn more about the product I'm working on and join our beta. Thanks again.